Okay, so after the Chinese remainder theorem, which helps us solve a system of linear congruences in one variable, the next natural step to take is to consider a single congruence with two variables. Linear congruence again, but with two variables this time. That is a congruence of this form: ax plus by congruent to c modulo n. Now, just like what we had seen in theorem 4.7, a condition for solvability of this congruence similarly is this: the above congruence is solvable if the greatest common divisor of a, b and n divides c. It's easy to see why, because if you go back to the theory of a congruence, a linear congruence where you have only one variable, that is, if your congruence is this, then we know that such a congruence is solvable when the GCD of A and N, not B, A and N divides B. That is because you know that when that happens, then B will be some integer k times this GCD, and you also know that the GCD of A and N itself is a linear combination of A and N. That is, you will be able to express this GCD as some, say, alpha A plus beta N for some integers alpha and beta. And that is why you will get something like this: k alpha A plus k beta N. Now you can clearly see that this thing is congruent to k alpha A mod N. And that's how you have k alpha A congruent to B mod N. So all of these things are possible because the GCD of A and N can be expressed as a linear combination of A and N. A similar thing happens here also. Here we have GCD of A, B and N because we have two coefficients instead of this one here. So this GCD itself is also a linear combination of A, B and N. If you go back to the theory of GCDs, there at the end of that section which discusses this greatest common divisor, you will see a small discussion about this, how to extend the notion of GCD from two numbers to three numbers and in fact any finite number of integers. So from that itself, you can see that this is the condition for solvability of such a congruence. You of course understand that here x and y are the unknowns and a, b, c are integers, n is a positive integer. In particular, this condition for solvability of the above congruence is satisfied if the GCD of A and N is equal to 1, or the GCD of B and N is equal to 1. Condition for solvability means this condition, that the GCD of A, B and N divides that integer C. If A and N themselves are relatively prime, okay, there is no common prime divisor between A and N. That's what being relatively prime means. Then obviously there is also no common divisor between A, B and N other than 1. I mean, I am talking about positive divisors. So automatically in that case, if GCD of A and N is 1, GCD of A, B and N will also be 1, and 1 of course divides C, and that is also the case if the GCD of B and N is 1. So if any one of these two things is true, then our congruence is solvable. And say this one is true, say A and N are relatively prime. Then what can we say? Actually, then how can we solve that above congruence? Suppose that A and N are relatively prime. We can rewrite this congruence slightly differently like this. AX is congruent to C minus BY mod N. Obviously, from properties of congruences, we know that these two congruences are equivalent. And now you look at this congruence and you look at this condition and you go back to the corollary to theorem 4.7 by the corollary to theorem 4.7, this congruence has a unique solution, and the uniqueness of the solution comes from the fact that the GCD of A and N is 1. If it is something else, say D, which is not necessarily 1, then this congruence would have D incongruent solutions. We have already seen this. But there is something else also that needs to be clarified here. What about this y? This y is not an integer. I mean, it is to be treated as an unknown. So we cannot just simply say as a unique solution and leave it like that. No, that won't make any sense. We have to continue like this. Has a unique solution for each of the n incongruent choices for y. What does this mean? You can put any value of y here. Y of course is an integer. You can put any value of y here, and once you choose a value, say y equal to 0, then the congruence reduces to Ax congruent to 0 mod n. Fine, you can choose some other value of y also, say y equal to 1, then the congruence will be Ax congruent to C minus B mod n. But because we are talking about the modulus n, so you can choose n values of y which are incongruent to one another, and those n values are 0, 1, 2 like this up to n minus 1. If you go beyond this, essentially those values again will come back because you are talking about modulo n. And that is why we say that for the n incongruent choices for y, for each such choice, you will get one congruence, and that congruence is going to have a unique solution modulo n. That means you are actually going to have n solutions depending on the values of y. It is somewhat like a single linear equation like this. If you have only one equation, no, there are infinitely many solutions of this equation, provided of course there are some conditions on this coefficient. Say for specificity, let me take x plus y equal to c. If someone asks you to solve this equation alone, there is no other equation, okay, what will you do? You can write x equal to c minus y. Then for every possible value of y, you will get a value of x, and thus you will get infinitely many ordered pairs of x, y values which will be solutions to this equation. The situation is like that here, except here we do not have equation but we have congruence. And because our modulus is n, we won't have infinitely, well, actually we will have infinitely many solutions, but the number of incongruent solutions can be at most n, and in this case we are going to get that. Now to better illustrate this idea, let us take an example. And that example is this. Consider the congruence 7x plus 4y congruent to 5 modulo 12. Okay, so if we express this congruence in that form, then it will look like this: 7x congruent to 5 minus 4y mod 12. Now we can choose any of the possible 12 values of y, and the corresponding value of x can then be found. The author has made the choice y congruent to 5 modulo 12. So essentially he is taking y equal to 5, but I say essentially because instead of putting y equal to 5, you can also put some other integer which is congruent to 5 modulo 12. In other words, if you choose integers from the same congruence class modulo 12, then you are essentially just doing one thing. Taking y congruent to 5 mod 12, we get So if you just substitute 5 in place of y, what will you get? 7x congruent to 5 minus 4 times 5. 4 times 5 is 20. 5 minus 20 is minus 15. Mod 12. However, in place of 7x, because you have 12 modulus, you can also write minus 5x minus 15 mod 12. Okay, modulo 12 7x is the same as 5x. Minus 5x. Now we can cancel minus 5 from both sides. Why? Because minus 5 is relatively prime to 12. So you can invoke one of the laws by using which we can cancel an integer from both sides of a congruence, provided the integer is relatively prime to the modulus. Otherwise also you can cancel, but then you will have to change the modulus, divide the modulus by the GCD, and those things are there. In this case, however, because minus 5 is relatively prime to 12, so we can simply cancel minus 5 and have this. So for the choice y congruent to 5 modulo 12, you have x congruent to 3 modulo 12. And these two things together give you one solution to your original congruence. So x congruent to 3 mod 12 and y congruent to 5 mod 12 is a solution. You can find other solutions also like this by choosing some other congruence class for y, the y variable. In fact, another solution has been mentioned in the text, which is this. Where again x is congruent to 3 mod 12 and y is congruent to 8 mod 12. And now we are going to see one result which is going to give us a condition, and when that condition is satisfied, you can solve a system of two linear congruences in two variables x and y. So this time in this result we are not going to consider one linear congruence in two variables, but two such congruences, a simultaneous system of congruences. And this is theorem 4.9. The system of congruences ax plus by congruent to R mod n, there is of course one modulus, and Cx plus dy congruent to S mod n has a unique solution if there is a condition. It is like having two linear equations in two unknowns. In school, we are taught how to solve such systems of equations by eliminating unknowns. Okay, we learned this technique of eliminating unknowns if we are given two equations in two unknowns. And an exactly similar technique we are going to use in the proof of this result. But before that, let's see the condition. If the GCD of AD minus BC and N is 1. There also, in that system of equations also, there is one such condition, namely AD minus BC should not be equal to 0. Here that similar condition takes this form. So I said that we are going to apply a similar technique. Here also we are going to eliminate unknowns. So we have these two congruences, AX plus BY congruent to R mod N and Cx plus dy congruent to S mod N. So what we now do, let us first of all eliminate y. For that, what should we do? You multiply the first congruence by D, the second one by B, and then subtract the second one from the first. In fact, let's just write that. Now, we are going to write in a slightly casual manner, not really very rigorous, like this. Now, D times the first congruence minus B times the second one gives us the following. So after you do this, what is the justification for you to be able to do this? The justification comes from the properties of congruences. Those parts in that elementary properties of congruences, they make sure that you can, in fact, in such situations, treat congruences as if they are equations, ordinary equations. You are then going to have AD minus BC, because D times this minus B times this. That will make y vanish, and you will be left with this times x congruent to dr minus bs mod n. Okay, so far we have not used that condition, but now we will use. Since the GCD of AD minus BC and N is 1, the following congruence has a unique solution Unique solution modulo n. Okay, we do not write that every time. That's understood when we are talking about congruences. When we say unique solution, that means unique solution modulo n. This congruence AD minus BC times Z. So in this congruence, the unknown is Z, congruent to 1 mod n. That's because the GCD of this coefficient and the modulus n is 1, which of course divides 1. So we know that this congruence has a solution, and because this GCD is 1, then modulo n there is a unique solution by the correlative theorem 4.7. Let this solution be, say, some integer t. Actually, there will be infinitely many such integers t modulo n, but you can just take any one of them. Now what we do, we are going to multiply both sides of this congruence by t. Now, if you do that, you will get this t times AD minus BC times x is congruent to t times dr minus bs mod n. Now, because t is supposed to be a solution, the only solution to this congruence, so AD minus BC times t is congruent to 1 mod n, and that's why this can be replaced by 1, which means that the left hand side of the congruence will be x. Minus bs mod n. So you see that you have found x actually. You know what x should be. That, however, is not the entire solution because you have to find y also. And that's why this time we are going to apply that same elimination technique but in a different way so that x gets cancelled. Because it is somewhat, there is a high chance that we will make some kind of mistake. So let me again write the original congruences. Mod n and c, why c here, r, cx plus dy congruent to s mod n. What will you do this time in order to cancel x? Well, we can do this. Say we multiply the second one by a, the first one by c, and subtract that first one from the second one, after multiplication. Now, c times the second congruence minus no, I wrote something wrong. Not c times the second congruence, a times the second congruence minus C times the first one gives us, because then only we will have AC minus CA, and here we will have AD minus BC. So again we are getting AD minus BC, but this times Y congruent to AS minus CR mod N. But now it's very easy, we already know about T. So you multiply both sides by T. When you multiply both sides of a congruence by an integer, there is no restriction on the integer. But when you want to cancel an integer from both sides, which is present on both sides, then you have to see that the integer is relatively prime to the modulus. So without any problem, we just multiply. And T times this is congruent to 1 mod N, so we get this minus CR mod N. So that's how we know that because of that condition that AD minus BC and N are relatively prime, our system of congruences has a solution whose X part looks like this and Y part looks like this. Actually, strictly speaking, you have to in fact go back to the original congruences and substitute these values to see that yes, you have in fact found solutions. Whatever we did so far, you see this single implication, that means implication. We have not been working with double implication. So we don't necessarily know if we can go back from these X and Y expressions to the original congruences. Essentially what we did is this. We assumed that X and Y exist, that is, there are such solutions given by X and Y. With that assumption, we then found out what X and Y should be, but that's actually not enough. You have to go back and put these expressions in these two congruences to see that yes, actually they are satisfying the given congruences. That I won't do, okay, that I leave to you. Instead, after showing that there is a solution, let us next show that it is unique modulo N. Because you remember, in the original statement, we are not only mentioning a solution but a unique solution. So let us next see that. To prove uniqueness, we will assume two solutions and then show that they are essentially the same. Next, assume that x1 comma y1, let me write a solution as an ordered pair, and x2 comma y2 are both solutions of the given system. Then what does that mean? That means several things. Let me write in short like this. Ax1 plus by1 is congruent to R modulo N. But simultaneously, ax2 plus by2 is also congruent to R modulo n. Have to mention mod n. In some cases, you can choose to not write mod n if it is understood what the modulus is. But the problem is that if you form a habit of doing this, then things may really become dangerous. You won't really feel like writing mod n after some time, and you just forget about mod n. You forget about the modulus, and then things start to fall apart, things start to go wrong. So it's better to write mod n. Similarly, we have Cx1 plus dy1 congruent to S, and at the same time Cx2 plus dy2 also congruent to S mod n. Now from these congruences, if we do subtraction, then we will next get these. This showing that the solution is unique is really not there in the text. It's not really very difficult, it's nothing difficult. So I think the author has decided that we should do it. He didn't even mention anything. From these, we next get this. So if you subtract this from this congruence is this congruent to R, from the this congruence that this is congruent to R, you get this. A times x1 minus x2 plus b times y1 minus y2 congruent to 0 mod n, because R minus R. Similarly, c times x1 minus x2 plus d times y1 minus y2 is also congruent to 0 mod n. Subtracting this one from this one. From the above two, congruences, we then get, now from these two congruences also we can apply a similar, we can get a similar thing. We can apply our elimination technique to these two congruences as well. For example, what we will do, we won't write anything explicitly this time, but we will just simply do it. Say you want to eliminate y1 minus y2. What will you do? You can do this. D times the first one minus b times the second one. That will get you rid of y1 minus y2. x1 minus x2 will remain, but with this. AD minus BC times x1 minus x2 will then be congruent to 0 mod n. And now you can almost guess what you should do next. Again, you multiply by that t. Multiplying 0 by t will give you again 0, and t times AD minus BC is congruent to 1. So you end up getting this. And this implies x1 is congruent to x2 mod n. So although the integers x1 and x2 may be different actually, but there is essentially no difference if you whether you take x1 or you take x2, because they are congruent to each other modulo n. So you don't get anything new in fact. Similarly, if one eliminates x1 minus x2, one will ultimately get, you can already see how y1 congruent to y2 mod n. So the solutions x1 comma y1 and x2 comma y2 are essentially the same solution. Modulo n, they are equivalent, so you haven't got really anything new. And that is why we say that the solution is unique. Okay. So now let us use this and consider an actual system of congruences. And that system is this. Says 7x plus 3y congruent to 10 mod 16 and 2x plus 5y is congruent to 9 modulo 16. Before we do anything, we have to find that GCD. Note that AD minus BC, okay, AD, that is 7 times 5 minus BC, 3 times 2 and n. So this becomes what? Minus 6 comma 60. $29. So this is 1. Yes, the condition of the above theorem is satisfied here. That means this system of congruences will have a unique solution modulo 16. And next we find that solution. Now we will have to go like the proof went. We have to eliminate one of the two unknowns. The author has eliminated y first. How can you eliminate y? You can, for example, multiply the first one by 5, the second one by 3, and then subtract the second one from the first one. Let me write it to make it clear. Now, 5 times the first congruence minus 3 times the second one gives us, it's going to give us what? Y won't be there anymore. It will give us 7 times 5 minus 3 times 2. Oh, so actually we will get that same thing. We have got this in the proof also. But on this side also we will have to do that same thing. So 5 times 10 minus 3 times 9 mod 16. So this will be 29x, and this is 50 minus 27 mod 16. Let me keep those two congruences, okay, and let me continue from here. $29x is congruent to 23 mod 60. Now this can further be simplified. That is, you can you can reduce 29 and 23 modulo 60, because 2 times 16 is 32, which exceeds both 29 and 23. So to reduce them modulo 16, you can just subtract 16 from them, both of them. So that will give you 13x congruent to 7, I think. Is it not 7? Yes. Mod 16. Now you can see, okay, now you will have to solve this congruence, and you can go back to the theory for doing that. However, simply inspecting what integer you have to use to multiply both sides so that you get something here that is congruent to 1 mod 16. In fact, that's what you want, right? So you will notice that 5 times 13 is 65, and 4 times 16 is 64. So 5 times 13 is congruent to 1 mod 16. So we multiply both sides of this congruence by 5. That will give us this. And 35 is itself congruent to 3 mod 16, because 35 minus 3 is 32, which is divisible by 16. That means we have found x. Now how to find y? The proof suggests that we go back to the original 2 congruences and then eliminate x. You can, however, do something better. You substitute this x in one of the 2 congruences. Like after finding one variable value, when 2 equations are given, you substitute that value in one of the 2 equations to find the value of the other variable. So you do a similar thing here. And in fact, I believe that's what the author also has done. Or he did, oh, I think he, okay, he did not do that. He actually again eliminated, used the original 2 congruences to eliminate x. Let us not do that, okay. Let's substitute 3 for x, say here. I think it will be better if we do it to this second congruence, because you will get a smaller number, you will get 6. So from the second congruence we get, let's do that instead, what we have decided here, and let's see what we get. I don't know what we will get. 2 times 3, we should get that same y. 5y is congruent to 9 mod 16. This means 6 plus 5y is congruent to 9 mod 16, and that means 5y is congruent to 3 mod 16. Now, whatever trick we applied here can also be applied there. But what do you have to do now? Because 5 times 13 is congruent to 1 mod 16. Multiply both sides by 13. That will give you this. Mod 16. So the left hand side will become y, and this is so 16 times 2 is 32. 16 times 3 is 48, that exceeds 39. And if you subtract 32 from 39, what do you get? 7. Is that what you get? Yes. Now let me see if I have got the same. Yes, y is congruent to 7. You can either use elimination or you can do substitution also. I mean, of course, you are ultimately going to get the same thing, but it's up to you which one you find convenient. I found this one convenient, okay. So I decided to do this, and that is why x congruent to 3 mod 16 and y congruent to 7 mod 16 is the unique solution to these two congruences, and the uniqueness is modulo 16. There will actually be infinitely many x and infinitely many y values that will solve the two congruences simultaneously, but all of them will give us solutions that are essentially the same, modulo 16. And this is where this section ends, and I believe the chapter also ends. After this, we have the usual exercises at the end of the section that we will solve next. Next Monday, of course, I have to go back to class 11 problems. But after that, the next Monday, we will solve the exercises. And the next upload is going to be this coming Saturday again. So that's just it for tonight. So until I see you next time, this is me, Lucifer from A Mathematical Room. Have a nice night.